Hello, welcome to Target IAS. I am Om Prakash Rajput, and today we will see our next topic: boundary conditions. So, what are these boundary conditions? Till now, we have considered the electric field or electric flux density only in a single medium. But what if the electric field is traveling one region, from one region? Suppose from this is region one and this is region two, and electric field is going from this region to this region, which is having different dielectric properties. So what happens to electric field is that remain same here, or it will be different in the other medium? We will find based on the boundary condition. If the medium changes, then what happens to them? So for electric field, for electric field, we can say that it is having one tangential component and one normal component. For any electric field, we can divide into two part, basically one tangential component and one normal component. Similarly, for electric flux density also, we can split into two parts, one tangential and one normal component. So and we can take a boundary, so that when the electric field is going from one region to another, suppose I am taking z equals to 0 line, z equals to 0 line, or we can take this as xy surface which is at boundary, for the which is boundary. So z less than 0 will be, suppose, medium 1, and z greater than 0 will be medium 2, medium 2. Here the electric field, suppose E1, having one tangential component and one normal component. Okay, and similarly for electric flux density, one tangential component and one normal component, here dn1. Okay, and here in this electric field, uh, E2, in the region, in the medium 2, the electric field having one tangential component and one normal component. Similarly for electric flux density, one tangential component and one normal component, like this. So are they same? Are E1 E2 same, or are D1 D2 same, or what is that? So let's see. For boundary, here, this medium has some different value for electrical permittivity. Suppose epsilon 1, or we can say epsilon r1, relative permittivity is different. Here epsilon r2. So what are the changes in when electric field is going from one region to another? So we find that on the boundary, on boundary, that is I am taking here z equals to 0 surface. So on boundary, tangential component, tangential component of electric field, or you can say electric field intensity of electric field, or of electric field, are continuous. What is that? What does that mean by continuous? That is, it will not change. So it means, continuous means equal. Continuous mean equal. So on boundary, tangential component of electric field are continuous. So we can say that the ET1, that is tangential component of medium 1 field, will be equals to tangential component of medium 2 field. Okay, so ET1 equals to ET2. Obviously their magnitudes will also be equal because they are equal in vector form. So this can be said that ET1 equals to ET2 on the boundary surface. Second one is the normal component, normal component of electric flux density. Normal component of electric flux density, or you can say densities, because two medium are discontinuous. Are discontinuous. Discontinuous mean, obviously continuous means equal, so discontinuous means not equal, but they are related. Normal component of electric flux density are discontinuous at boundary surface boundary surface by an amount equal to surface charge density on the surface charge density present on boundary surface. So what does this mean? You see, what is this? Normal component of electric flux density, normal component of electric flux density are not equal, they are discontinuous, but it is given that it is discontinuous by an amount equal to surface charge density present on the boundary surface. It is discontinuous by an amount by surface charge density. That is, we can say that they are related like this, that suppose this is magnitude of electric flux density and this is magnitude of, if we take the difference of both the electric flux density in medium 1 and medium 2, then we will get what is we will get the surface charge density, because that is the amount by which they are what, they are discontinuous. That is the amount by which they are discontinuous. Suppose if rho s equals to 0, so if there is no surface charge density on the surface, if rho s equals to 0, then what happens? dn1 magnitude will be equals to dn2 magnitude, right? So we can say that in this case dn1 will be equals to dn2. Okay, and similarly we can also say that uh, epsilon not epsilon r1 en1 equals to epsilon naught er2 equal en2, right? By using the relation between d and e, here we will get epsilon r1 en1 equals to epsilon r2 en2. So we can use this relation to find, if to find the electric field of other medium if one medium electric field is given to you. Okay, now we see a special case, which is if the medium, suppose this is medium 1 having a dielectric of relative permittivity epsilon r1, and here medium 2 is a conductor. Medium 2 is a conductor. Now you know that for a conductor, suppose this is z equals to 0 surface, again I am taking, for a conductor there will be no electric field inside a conductor. There will be no electric field inside a conductor because current density is given by J equals to sigma E, and for a conductor we take sigma is very high, that is conductivity is very high. So if this conductivity is very high, then E equals to J by sigma. So when this tending to very high, this will be 0. E will be 0. So there will be no electric field inside a conductor, and obviously as there is no electric field, the D value will also be 0 inside a conductor. Okay, So the D value, E value will be inside a will be 0 inside a conductor. Okay, all the charge inside all the charge on the conductor will be present on the surface of the conductor. There cannot be any charge inside a conductor. Okay, there cannot be any charge inside a conductor. All the charge will be spread over the surface. Okay, so this is in the medium 2, so I will write this as E2 is equals to 0. Now this is having two components, that is Et2 plus En2. They are what? 0. And you can individually say that Et2 is equals to 0 and En2 is also 0. Now here in the medium 1, the electric field is E1, which is not 0. Okay, which is not 0. Here also one tangential component plus one normal component. It is actually medium 1. So I should write Et1 and En1. This is equals to E1. Now you know, as I have told, that the tangential component is continuous, which means Et1 equals to Et2. And as here inside a conductor, the tangential component will be 0. So this means what? Et1 is equals to 0. So this means that the tangential component of the electric field is 0 for a conductor dielectric boundary. For a conductor dielectric boundary, the tangential component of electric field is 0 for conductor dielectric boundary. The tangential component of electric field is what? 0. Okay, so now the tangential component is 0. So now what about the normal component? You know that dn1 minus dn2 is equals to rho s. dn1 minus dn2 is equals to rho s. Okay, and here we can relate this as epsilon naught epsilon r1 en1 en1, and I can write this as magnitude minus, as this en2 is 0. Here en2 is 0. So what is that? dn2 will also be 0. dn2 will also be 0. So this is 0 is equals to rho s, right? So we can say that here we can also say that the magnitude of the displacement flux density is equals to displacement flux density on the medium 1 will be equals to the surface charge density on the boundary surface. And similarly you can find the normal component of electric field of the in the medium 1 by this expression, right? You can find the magnitude of this normal component. So this is the relation between conductor dielectric boundary surface, that inside a conductor electric field is 0. So you can use the relation in the following ways, that electric field inside a conductor will be 0. So Et1, that is Et1 equals to Et2 equals to 0, that is tangential component of the electric field is 0, and the normal component of electric flux density in the dielectric medium will be equals to surface charge density on the boundary surface. Now let us see one question based on the boundary condition. Medium 1 has electrical permittivity, this, and occupies the region to left of x equals to 0 surface. So this is the boundary surface which given in the question, x equals to 0. Medium 2 has electrical permittivity of this 2.5 epsilon naught and occupies a region to right of this surface. और मीडियम वन में इलेक्ट्रिक फील्ड गिवन है E1 is equals to 2ax cap minus 3ay cap plus az cap. Then E2 in the medium 2 is. So what is the E2 in medium 2 from the given option will be correct. So let us see which is the answer. Okay, we have to apply boundary condition. So suppose I'm solving it here. So here given value of E1, if I write, it is 2ax cap minus 3ay cap plus az cap, and you have given boundary surface x equals to 0 boundary surface है. So normal component क्या होगा x equals to 0 boundary surface के लिए? Obviously x direction में जो component है वही normal होगा इस x equals to 0 boundary surface के लिए. So इसका जो normal component है en1 will be 2ax cap, and the other one remaining will be tangential component, that is minus 3ay plus az cap. Okay, so from the given option you can see uh, wait, so in medium 2 what happens? E2 is the electric field which is having component Et2 plus En2, and you know that at boundary Et2 is equals to Et1. At the boundary surface Et2 tangential component is continuous, so I can write this as uh, minus 3ay cap plus az cap. So you can see from the given option there is only one option in this tangential component, that is this component minus 3ay cap plus 1.0 az cap. So you can directly take the answer which what is correct option. So anyway, let's find out the normal component. So how the normal component is related? It is related by dn1 minus dn2 is equals to rho s. Here no charge surface charge density is given, so we can take rho s equals to 0. So this dn1 will be written as epsilon 1 and en1 is what? 2ax cap, and epsilon 1 is 1.5 epsilon. So I can write it as epsilon 1 en1 equals to epsilon 2 en2. So epsilon 1 is what? 1.5 epsilon naught, and en1 is 2x cap. Epsilon 2 is 2.5 epsilon naught. 2.5 epsilon naught. En2 is we have to find out en2. So if you solve this here, 1.5 divided by 2.5, it will be 1.5 divided by 2 and multiplied with 2. So it will be 3 by 2.5 ax cap equals to en2. So if you solve this, you will find that en2 will be what? 1.2 ax cap. So this is also, I mean, you can find out. So this is the correct option. Okay, so here one more question. Displacement flux density at a point on a surface of perfect conductor, you see perfect conductor, is d equals to this is given on surface. So this is in coulomb per meter square and is pointing away from the surface. So surface charge density at the point will be surface charge density at that point will be. So what will be the surface charge density at that point? So you know that on a conductor surface what happen is that dn1 minus dn2 equals to rho s, right? And for a conductor surface, suppose this medium 2 was the conductor, so dn2 will be 0, so dn1 will be equals to what? Rho s. dn1 will be equals to what? Rho s. So here dn1 is given and we have to take what? Its magnitude. So we can take the magnitude of dn1, what it's given? It is given this. So its magnitude will be twice of 1 square plus root 3 square, twice of 1 square plus root 3 square equals to rho s. And if you solve this, so it comes as 142 rho s equals to 4 coulomb per meter square. Because, and why we have taken this plus 4 not minus 4, because in the question it is given away that it is pointing away. So for a surface which type of charge the electric field or the electric flux density point away, it is positive charge only. So that's why the surface charge density is plus 4. Okay, so this is all about the boundary condition. Now we'll see a few more things in electrostatics which are remaining. So let us first see what is a homogeneous medium. For homogeneous medium, the the any medium will be characterized by some constant, that is electrical permittivity and magnetic permeability and conductivity. So for a homogeneous medium, we will see only these properties right now. So electrical permittivity, permeability and conductivity constant are constant for homogeneous medium. If it is a non-homogeneous medium, if it is a non-homogeneous medium, so what happen is, for non-homogeneous medium, these values won't be constant. They changes from location to location. Values will change from location to location. At every point there will be different values for permeability, permittivity and conductivity. So basically we can say that these epsilon, mu and sigma will be function of some x, y, z, and for a non-homogeneous medium. So now we will see one equation, that is Poisson equation. Poisson equation. So Poisson equation is what? They will be used for solving the potential and for finding the charge density. So let us see what is Poisson equation. As you know from the Maxwell's first equation, that was del dot D equals to rho v. Del dot D is equals to rho v, and you also know now that D is equals to epsilon E. D is equals to epsilon E. So suppose this is first equation, this is second equation. If I put this equation here, D value, so it will be del dot epsilon E equals to rho v. Del dot epsilon E is equals to rho v. Now you know that uh, E E is equals to what? Minus del V, that is gradient of the potential, gradient of the potential. So if you put that E value here, so it will be del dot epsilon here minus gradient of the potential, minus gradient of the potential equals to the charge density. Now we can arrange some terms here so that it looks like, I can take this minus sign on the right hand side because it is independent of the differential operator. So I can take this out and it will be looking like, then equation will look like some del dot epsilon del v equals to minus rho v. This will be the equation. Okay, this equation here, this equation is Poisson equation. This equation here is Poisson's equation in non-homogeneous medium. In non-homogeneous medium. Non-homogeneous medium. So in non-homogeneous medium, you can use this equation as Poisson equation. Now for a homogeneous medium, what happen is, I told you that epsilon, mu and sigma are constant for homogeneous medium. So I can take this epsilon common, I mean out of this differential operator, and I can write it as epsilon del dot gradient of V equals to minus rho V, equals to minus rho V. And using the properties of vector differential operator and vector operations, this del dot gradient, that is, what is this basically? It is basically divergence of gradients, which becomes del square V, del square V. And I can take this epsilon in denominator of this. It can be written like this: del square V is equals to minus rho V by epsilon. This is Poisson's equation, Poisson equation in homogeneous medium. Okay, in homogeneous medium, because I have taken this epsilon out of this vector differential operator, because epsilon value will be constant for homogeneous medium. So this will be the this will be the Poisson equation in homogeneous medium. But in non-homogeneous medium, I cannot take this epsilon out of from the this vector differential operator. So you have to be careful about non-homogeneous and homogeneous medium. Now if I put if I take this rho v 0, that is, if the volume charge density is 0, if the volume charge density is 0, if rho v becomes 0, ठीक है, rho v 0 होने का मतलब ये नहीं कि कोई चार्ज प्रेजेंट नहीं है. There can be any like q point charge, suppose, or line charge or a surface charge can be present. There can be a line charge, surface charge or a point charge can be present. So अगर rho v 0 हो गया, then what happens to the equation I have written for non homogeneous medium? Here on the right hand side it will be 0, so only del dot epsilon del v will be remaining. So I can write del dot epsilon del v equals to 0. This equation is known as Laplace equation. This equation is known as Laplace equation. This equation will be Laplace equation. Okay, and Laplace equation for, obviously, for non-homogeneous medium, non-homogeneous medium. And similarly for the homogeneous medium, del square v is equals to 0. Del square v equals to 0 because I have taken rho v as 0. This will be the Laplace equation for homogeneous medium. Laplace equation in homogeneous medium. Okay, so these now from using from these equation, if you want to find out for any surface, if you find if you want to find out the potential, you can use this equation, Laplace equation, for a surface which is having no surface charge, no volume charge density. Okay, or if it is having volume charge density, then you can use this equation for homogeneous medium and find the potential, right? So these will be used to solve the potential. And using that potential, you can obviously find then the electric field and then the displacement flux density, right? Or you are given potential, you have to find the charge, volume charge density, line charge density. You can find those things also. So using these equations, the Laplace equation and the Poisson equation, we can find potential and electric flux density or charge problems like that. Now let us see this one question. Basically this is not a question, this is some type of derivation. You have to find VED for spherical capacitor between R equals to A and R equals to B, surface shown below. Find CAB. After finding VED, you have to find CAB, and the given value of V at R equals to A on this surface is V naught. Okay, and for r equals to b, it is 0. So we can say that it is grounded. It is grounded at on this surface. R equals to a, value of this is v, potential is v naught, and medium is homogeneous, and rho v is given as 0. Rho v is given as 0. So if you see, we can use here uh, Laplace equation, because homogeneous medium and rho v equals to 0. So what the Laplace equation says is del square v equals to 0. Laplace equation was del square v equals to 0, right? So what is this del square v basically? Del square v is nothing but a Laplacian operator. If you remember the formula for Laplacian operator in spherical coordinates, because this is a spherical capacitor, so it was 1 by r square del by del r, here r square del v by del r, plus 1 by r sine theta, 1 by r sine theta, del b del by del theta, del b del by del theta, and sine theta del v by del theta, plus 1 by r square sine theta del 2v by del phi square. This is the formula for Laplacian of a scalar, and this is equals to 0 by which equation? This is Laplace equation. Laplace equation. So we are using Laplace equation to find first potential, then we will simply find electric field. So here the value of V is given in terms of basically which are depending on R value. So we have to consider only the R component from this. So we have to consider only this component. This component becomes 0. So only things remaining is 1 by r square del by del r square del v by del r equals to 0. Okay. So we can solve this. Here r square will go to the right side, and after that integrating on both sides, what it will become? Del by del r, here r square del v by del r, okay, with respect to this. So integration of 0 d r. So if you integrate this, it will come as this integration differentiation will get cancelled, and the remaining thing will be r square del v by del r, r square del v by del r equals to 0 plus some constant, equals to 0 plus some constant, right? So now we will do another integration. We can do another integration here. It will first, before integration, let us do some arrangement. So after rearranging, it can be written like this: del v a by r square del r. Now integrating again on both sides. Now if you integrate, what will happen? So integrating del v is equals to integrating a can come out of integration because it is a constant. So here it will be v, and what will be here? It will be a 1 by r minus 1 by r, and plus some constant, plus some constant. Now we will apply the initial condition which were given to find the value of a and b. It was given that at at r equals to b, v equals to what? 0. At r equals to b, v is equals to 0, right here. So we can use this. So we will put r equals to b. So it will come 0 equals to minus a by b, because r in the place of r it will be b, and B, the capital B. So this value of B, capital B, will be A by small b. Okay, we will use this value. Now the other boundary condition was at r equals to A, V is equals to V naught. So we will use this. V naught is equals to minus A by small a plus B. B value is A by B, right? So the value of A will be the value of A will be, if you write, it will be V naught upon minus 1 by A plus 1 by B, minus 1 by A plus 1 by B. And you can similarly put the value of A here and find the value of B. So the expression for V was simply this, with A and B as constant, which we have found using the initial condition, right? So if you put the value of A and B in the expression of V, which was minus A by R, so minus A, this will be minus V naught by R into this minus 1 upon B minus 1 upon A. So this thing can be written as 1 by B minus 1 by A plus B. B is nothing but A by B. So I have to write V naught by 1 by B minus 1 by A again, and a 1 by B, A by B. Okay. So here I can take few things common, like 1 by B minus 1 by A, and the remaining thing will be 1 by B minus 1 by R. So this will be the expression of potential of spherical capacitor in the given condition. Okay, this will be the value of V. Now we have to find electric field. As you know that electric field is nothing but minus gradient of potential, right? So we have to just find the gradient only. So we have to find the gradient. For that it will be, and only the R component will be there, because there is no theta, no phi. So if we do del V by del theta and del V by del phi, it will be 0. So simply just taking the gradient formula, that is del V by del R AR cap, the other components becomes 0 because there is no value of theta and phi. So in the expression of V, you can see that V naught by 1 by B minus 1 by A are not dependent on R, they can be taken out. So it will be minus V naught by 1 by B minus 1 by A into del by del R of this expression, 1 by B minus 1 by R and AR cap. So after solving this, here 1 by B differentiation with respect to R will be 0, and for 1 by R it will be minus 1 by R square. So it will be minus minus plus. So the final expression will be V naught by minus V naught by 1 by B minus 1 by A multiplied with 1 by R square AR cap. This will be the expression for electric field. Okay, so if I write here, it will be minus V naught by 1 by B minus 1 by A. You can write R square here, and the direction is AR cap. This is the expression for electric field. Now you have to find displacement flux density. Just multiply it by the epsilon value. So if I consider the electrical permittivity as epsilon, so simply it will be epsilon E. So it can be written as minus epsilon V naught by 1 by B minus 1 by A R square AR cap. And after that, after finding V, E and D, you have to find the CAB, that is the value of capacitance between those A and B spheres. So For capacitance value, what was the definition of capacitance? It was charge divided by potential between the plates or the surfaces. So Q by VAB. VAB is nothing but we have just found. And what will be Q? From Gauss law, you know that D dot ds is equals to Q. Flux crossing through a surface will be equals to the charge enclosed. So D dot ds equals to Q. So in place of Q I can write this D dot ds, and in place of VAB I can write the expression of V, which was, or I can write simply it was VAB, so VA minus VB. And you know that for VA it is given V naught, and for VB it is given 0. So you can simply write it as, if I first write VA minus VB, then I will write in place of D, this expression, the above expression can be written here, minus epsilon V naught by 1 by B minus 1 by A R square AR cap. Now what will be the differential surface vector? So as this is AR cap, so the differential surface vector should also be in the AR cap direction, and for that the differential surface vector is R square sine theta d theta d phi. R square sine theta d theta d phi AR cap. Okay, so it will be the value of D dot ds, right? So it is not just from Gauss law, it is basically, it is from actually. So this will be the value, and so anything remaining here, D value is here. Okay, now in place of VA we can write V naught, and in place of VB we can write 0, and we can simplify this above expression. Here few things are getting cancelled. Here the value of R square and R square gets cancelled. AR cap dot AR cap will be 1. The things remaining will be epsilon naught V naught. This thing will come out of integration because it is independent of this integration. So let me first write what will be remaining. So here it is a minus sign, epsilon naught V naught divided by 1 by B minus 1 by A, and this V naught will also come here, and integration sine theta d theta d phi. This will be the thing which is will be remaining. So here you can see that uh, this value will be, basically have to cancel V naught, and V naught will get cancelled. So the remaining thing is minus epsilon 1 by B minus 1 by A, and after integrating this sine theta d theta integration d phi, the value of phi will be 0 to 2 pi, value of theta will be 0 to pi. After solving this minus sign can be taken in the bracket, so it can be written as minus 1 by A minus 1 by B, and here sine theta after solving minus cos theta, and it will be 2, and here after solving this integration it will be 2 pi. So the value of CAB which is coming is 4 pi epsilon 1 by A minus 1 by B. I hope you remember this expression which we have found in the previous video for the capacitor, for a spherical capacitor. It is the expression. So in this way also we can find the expression for capacitance and other things also, V and VE and D. Okay, so that will be all for today. We will meet in the next lecture and we will see few questions on the electrostatics. So this is all about the electrostatics part, and after the numericals we will start doing magnetostatics. Thank you.